getting it over with. This is good. I had a few people doing the National Spanish Test, and it looks like Claire, I think, is doing that too, and Nabil is out. Amber? You did watch. Would you like to come up and do the intro? Okay, introduce us.
What's up, chemistry world? Chem Daddy here is going to teach you about trends in atomic radius.
That was nice. All right. These are, and unfortunately we have to do it in English today, not in Spanish. Because, well, maybe we get some of each. Here's where we are. We finished with this yesterday. I show you this. I really like this, but I wish, I guess, once I have this up here, that maybe I could just come up with a picture that has only the main group elements, not the transition metals. The transition metals have funny things happen. It doesn't give us the nice clean trends that the main group elements tend to do. These in here, especially down when we get to the bottom, you see that on the left, lanthanum and these elements start kind of big and then they get smaller, but then they kind of get bigger again, even within these, before we get to TL, which starts the main group block again. And you can tell that there's a bit of a difference here with palladium and then silver. They get real small, and then why do they jump like this? I don't know. I don't know what's going on with those atoms. But the general trend is for atoms to start big in size, and as we go to the right, they get small. You'll notice that this is the opposite trend of the ionization energy. Ionization energy, the atoms start small. Well, they start with a low ionization energy, and as we go across, they get higher and higher. And that's because as the atoms are getting smaller, it's more and more difficult to remove an electron. Why is it that the atoms are getting smaller? Well, we think that, in our best judgment on this, is that within a row on the periodic table, atoms are filling electrons into the same energy level. The same energy level. And that is the key, because as we go to the right across the row, there's an increase in the number of protons. So the nucleus is getting more positive. The electrons, yes, are being added, but they're being added to the same energy level. So even though there are sub-levels within the energy level, and it really does kind of matter down here, as you see, when we finish the D's and we start the P's, they do kind of get bigger again, but there's a lot of shielding going on down there too, which makes a difference. But electrons are being filled into the same energy level, and that outer energy level, that negative cloud on the outer energy level, gets drawn in as we go across because the nucleus is becoming more and more positive. And so because of that, we think that atoms are getting smaller for that reason.
What about the new group F elements?
There's no need to know what trend those have. They're rare elements anyway, and we don't really care about their size. The reason that we even do this business about who has a big size, who has a small size, who has a big ionization energy, who's got a small ionization energy, when we start talking about bonding, that stuff kind of matters. But we don't bother with the main group elements, like those bottom two rows, because we don't ever do any chemistry with them. I mean, when did I ever talk about europium and a reaction with europium? You can name any of them, even uranium. Everybody knows uranium, but we have never done anything with uranium in here. Those are rare elements, and so we don't bother with them. Okay. The next slide gives us this business about, as we go down a family, the picture is the same, but as we go down a family, without exception this time, atoms are getting bigger as we go down a family. And that's very easy to explain because, yes, the nucleus is bigger and more positive, but electrons are being added to a new energy level. So every energy level, the electrons are farther out, and the more energy levels you have, the less the outer electrons can interact with the nucleus. You got the negative electron clouds from the electrons, and they want to be attracted to the nucleus, but the more and more layers of electrons there are, the term that we use is shielding, the more of a shielding effect there is. And the shielding effect, I know I mentioned it yesterday, it is very much responsible for why the electrons are easier to take off the farther you go down. The atoms get bigger the farther you go down. The electrons just can't be held as tightly the more layers there are. Think of the shielding effect like this. Justin Bieber is going to come to town, and we all are going to take a field trip to the Bieber concert. Matt, sound good?
Yeah.
J. Deep, we're going to go to see Bieber?
Let's get it.
All right. So we all think, okay, let's get together early, like 5-6 hours early, so we can get to this concert and be in the front row. Maybe they don't have pre-sales and assigned seats. So we want to be in the front row so we can be right there next to Bieber. So we all get together. Oh, yeah, this is going to be great. And we get into our car and we jump on the highway, and the traffic is terrible. And we wait and wait and wait on the highway. And we wind up getting there late for the concert. This is not good. I'm sorry, guys. We were looking forward to this. Well, the traffic was bad because everybody got on the road before we did. So we're late. We are not first row. We're not second row. We're not anything close. We're out by the Porta-Johns, right? So these people around here, they get the full effect of the concert. They were lucky enough to get there, get the first row seats. They're like the inner electrons, man. They can feel the nucleus. We're way, way, way in the back. We don't get the same experience. We can't tell our grandkids that we were front row for Bieber. You know, we're like, well, yeah, we heard him, but we can barely see the guy. That's what the shielding effect is. Way in the back, you can't sense the nucleus like the people up in the front can. Just like the atomic radius is very much dictated by the shielding of the inner electrons. That's an old picture too, isn't it? He's a youngster in that one. Okay, so just so we can be clear on this, as we go up and right on the periodic table, atoms get smaller. Look at helium. Look how cute that thing is, barely a dot. And then down here we have, well, francium really. I always call francium the big boy. I have Andrew Habib in my last hour. I said, francium is the Andrew Habib of the periodic table. It's a big, bulky atom. It's huge. So that's a very clean trend in general. It's cleaner. Remember we had with the ionization energy, there was the exception, that nitrogen-oxygen exception, the beryllium-boron exception. This one is pretty clean. So that really is the story on atomic radius. The next trend that we'll talk about, this is the second to last trend. We'll talk about electronegativity now, and then we'll get to atomic radius, not atomic, ionic radius, and that'll be it. So electronegativity, oops, I did that wrong. Electronegativity's definition is the tendency for an atom to, when it's bonded, to yank bonded electrons toward itself. It's really the attraction for bonded electrons that an atom has. It's only measured on a relative scale. You can't take an instrument and measure how good an electronegativity of an atom is. We just have to look at, okay, when fluorine is bonded to oxygen, who's got the electrons more toward themselves? Then when oxygen bonds to nitrogen, who's got the electrons more toward themselves? So it's a relative scale. Notice the electronegativity in the y-axis, no unit. We see clearly who's the highest. And I love electronegativity because the trend is so nice. And I don't know why it says P block. There are S electrons in there too. So assume that the black dots are S and P's, what I would consider main group electrons. There are even some F's on here. And you can see some craziness happens with the D's. But in general, with the main group elements, on the left side, the electronegativity starts low, which means they have a low attraction for electrons. And as we go to the right, the electron attraction clearly goes up. Then we start a new row, and we start low again, and we go up. Pretty much without exception with the main group. There are some funny things that happen. That thing right there is weird. And then that, let's not even deal with that. Now it says at the bottom of this slide, which you can't see right here, most of the noble gases, the smaller noble gases, helium, neon, argon, they don't make bonds. They don't get into any compounds. Some of the bigger noble gases, krypton, xenon, radon, they can bond. They're typically endothermic. You've got to put a whole bunch of energy into them to get them to break up their electron, the very stable electron configuration and share, but they can. So we would say that the elements like the noble gases that don't bond, they don't have values for electronegativity. You wouldn't say that they're zero, you'd just say there's no value for them. So this is the same trend as ionization energy. As the atom gets smaller, the electronegativity goes up. The more attraction for electrons those atoms have. Now keep in mind, as the atomic radius is getting smaller, as we go to the right, atoms are getting smaller and smaller, they're getting smaller because those outer electrons have a very strong attraction to the very positive nucleus within that energy level. So you would naturally assume that bonded electrons would also have the same very strong pull. That's what electronegativity deals with. Okay, so the trends are like this. Across a row, the electronegativity is increasing because atoms are getting smaller. The electrons are drawn more toward the nucleus of the smaller atom. I think you'll find the chapter exercises to be pretty simple with these periodic properties, except maybe for the electron affinity. There's some zingers on the questions on electron affinity. So electronegativity and ionization energy have exactly the same trend. Ionization energy's got those couple of exceptions, but generally up and right on the periodic table, those values are going up. As atomic radius gets smaller, ionization energy, electronegativity go up, the opposite trend. And then down toward francium, atomic radius is big, where ionization energy and electronegativity are small. And it really just is dictated by the size of the atom. One other thing that I would mention, take a look at what happens as we go down a row. Just at the data, fluorine is the top in its row, and then it goes down to chlorine, and then down to bromine, and down to iodine. So the attraction for electrons is not as much as we go down a family, which you would expect because the atoms are bigger. So there's no big surprise on this one. Down a family, electronegativity decreases because the electrons on the outermost shell are farther from the nucleus. They're shielded. They can't feel the nucleus as much. So it can't attract electron. Yes?
So what would be more electronegative, N or S?
So S is farther to the right, but N is farther up, right?
Yeah.
N has a smaller radius. I would I know that N is, and we can see on here, fluorine, oxygen, nitrogen is right there. Sulfur is right there for chlorine. Yep.
Okay.
The highest electronegativity, you should know these. FON and Cl, you've heard that before. Those are the highest. No, when you learned about bonding in Chem 1, you learned about Fonkel. FON and Cl. Yep. They make polar bonds because they have such a difference in electronegativity with everything else. They kind of hog the electrons that are shared between themselves. Okay. Now the last thing in chapter 7 is ionic radius, or ionic size pretty much. When an atom forms an ion, its size changes significantly. And I'm going to just change this up again. I like this graphic. It kind of gives us a relative size when things become positive and then when things become negative. But especially what you need to know is this. When an atom forms a positive ion, it always gets smaller. When an atom forms a negative ion,